Hi everyone, I'm Richard Kueng from Austria, and I'm super happy, excited, and also a bit nervous to be here and granted the permission to speak a bit about complexity and quantum information theory to you. Okay, so thank you very much for the invitation and also to the organizers. This is a great event. Thank you all for being here. Maybe before I start, also a bit of a disclaimer. I would very much like to be a theoretical computer scientist. I tried very hard, but I'm not really. I actually studied chemistry before deciding that I was a very bad chemist, and then moved over to high-dimensional probability theory and randomized algorithm design and quantum computing. So some things that Heiko said resonated very strongly with me, for example, like these probabilistic ideas that Roman Verschinen is using, and also things we heard today by Amir regarding information theory resonate strongly with me. But when it comes to proper TCS, I guess almost everybody of you beats me. And so I also took the liberty of maybe interpreting the task of talking to you about quantum information and complexity a bit in my favor. There are several ways of telling the story. I guess all of them should start with a crash course on quantum information theory and quantum computing. This is a topic of today's lecture, but then there's different avenues to take. And one of them, a beautiful avenue to take, is to talk about quantum complexity classes, like the generalizations of P and NP, but I would truly feel like an imposter if I did that with Alex in the audience. So I instead want to talk about complexity of quantum circuits and quantum states in a Kolmogorov type of way, kind of like incompressibility and counting arguments, and how you make them in the quantum realm. Okay, and I did that on purpose because this is something where me and my colleagues have also contributed, and I think there's powerful underlying randomized proof techniques that are generally applicable, and I want to use these lectures to teach them to you. Okay? So before we start in earnest with the crash course on quantum processing units, you already saw me writing on the blackboard, and I apologize, it's terrible. I know it's too small, I know it's ugly, and I also know I can try, but I won't make it much better. So I have a peace offer for you. I actually hit the last couple of days and wrote approximately 30 pages of clean lecture notes with illustrations. And Alex was so kind and published it on his GitHub account. So the first thing I encourage you to do now, especially if you're in the back, take up your laptops, go to this GitHub page. It's GitHub, it's AB Grillo, one of the organizers, GitHub/io/Kueng, my last name.pdf. You should see LaTeX lecture notes for the next 3 lectures here, and this is my peace offer for you for failing to write nicely on the blackboard. Okay? Maybe can one of you kind of like raise their thumbs if you can get kind of like access to the PDF? So yes, it works. Great. Okay. And then when you fire up the lecture notes, you also kind of like see the grander plan that I want to do. We have 3 lectures. And today I'm going to introduce quantum information and computation kind of like the way I usually do it in computer science lectures. This might be redundant for some of you. Maybe I can quickly ask, can you dare to raise your hand if you worked on quantum information or computation before, or kind of like 2 classes? Very good. Can you raise it higher? Great. For those of you who haven't done that, remember who raised their hands. You can ask them questions later. You're also very, very welcome to ask them to me. Okay? But there is some kind of like expertise and experience in this room. And so kind of like you're not alone, but I still want to kind of like just start from the beginning to not lose anybody of you, okay? And this is really important for me, so also I encourage you to really kind of like raise your hands during the lecture or even interrupt me if there's something that you don't think is quite clear. In my experience, if you find something not quite clear, at least 10 other people also do. And if you kind of like stop me and give me the chance to elaborate, I can kind of like catch everybody back on track. Okay? So without further ado, now let's properly kind of like talk quantum computing and quantum information. And there's various ways of introducing this. I think there's no right and wrong way. The way I prefer is somewhat of a hardware design and electrical engineering type of way. Just for historical reasons, the circuit model of computation lent itself very well to be transferred into the quantum realm, whereas if you want to start with a Turing model of computation, it's kind of difficult. So I will really kind of like take an electrical engineering approach, and we will kind of like look at boxes and circuits that I tried to draw very poorly here, and if you fire up the lecture notes, you should see a nice version of this graph. Okay? But on a very high level, what is a quantum computer, or more precisely, a quantum processing unit? It's a way of processing information, and on a high level, it's not so different from the hardware or the chips that we use today. The input is a bit string, much like in a normal chip, in a Boolean circuit. And if you have a chip of size n with n qubits, the quantum generalization of bits, you can input a bit string of length n, like a normal Boolean circuit. And on the other end, once the circuit has done its computation, you are also guaranteed to get a bit string back. In the easiest case, an n-bit string. In general, this could be different, but let's stick to kind of like circuits with n inputs and n outputs. They are general enough for our purposes. Okay? And so what happens in the middle? And now you already see kind of like the electrical engineering or hardware approach. This looks a bit like a circuit, right? Kind of like we have a set of elementary gates, and we combine them to create more difficult and elaborate logical functionalities on these n bits. And the one thing that is weird, but I actually stand by it, is that I draw circuits from right to left. So for me, the arrow of time or the information flow is from right to left. Maybe I'm just a weirdo, but I have my reasons. And throughout this lecture, you should see why. And the first one, who kind of like shouts the reason why I write them from right to left, gets a bottle of wine from me, okay? You might know it now already, but kind of like please kind of like wait for the moment when you will see in the lecture why I do it, and then raise your hand and tell me why, and then you win a small prize. Okay? But this is kind of like the high level idea. So it's bit strings in, bit strings out. What is the interesting part of it? Well, this computation in the center does not quite work with transistors or logic as we know it, but it is our ambition to really kind of like scale down these processes to the smallest possible scales. Like think of individual atoms, individual photons, like the smallest constituents of the universe that we can still use to encode information in. Like for example, you can encode binary information into an atom by assigning the ground state to 0 and the first excited state to 1. Okay? So in principle, it's kind of like a drastical way of miniaturizing such that we can run this central part of the computation on the level of individual atoms or photons. And on a high level, why do we do this? Because different rules apply. Kind of like there, the rules of quantum mechanics describe what's going on, and this is very different from the macroscopic physics that describes how transistors work. And on first sight, this is a very big challenge, because it's very difficult to build such a computer. If you want to have n qubits, and you want to use atoms for the n qubits, you have to trap n atoms in the air somewhere so that you know where they are, and then you encode binary information. And then these kind of like operations require you interacting with these atoms. Okay, so this is very challenging. It's small, kind of like you really have to work hard for every qubit. And it's also slow, because kind of like the way you compute is you interact from the outside on these microscopic information carriers and force them to behave in a certain way. This is much, much slower than how electricity or current goes through a chip, basically at the speed of light in medium. So on first sight, this is challenging. Small and slow. So why do we care? The upside is that a different model of the universe applies there, quantum mechanics, and this gives us different functionalities. And so in a hardware model, you have a more expressive set of elementary gates. So there's more elementary logical functionalities. And this might change the rules of computation to some extent. And I always like to compare it with kind of like Lego, building Lego. I'm a big Lego fan. Kind of like if the task is to build a huge spaceship and I only get very basic building blocks, it might take me much, much longer, and it might require much more bricks in order to get the final result. Whereas maybe some of you has special parts directly ordered from Lego, and you can build shortcuts. And then there is at least the possibility of arriving at the spaceship with way fewer bricks, and then it doesn't matter if you build slower than me, if you are kind of like much more efficient. And this is kind of like the overall idea. Okay? Is there questions or comments or concerns at this point? Doesn't seem to be the case. So let's kind of like discuss and kind of like venture into this different world of circuits. And please stay with me, let's do it at the level of circuits and look at some elementary functionalities. Some of them are familiar and some of them are maybe unfamiliar that you can do with such quantum circuits. Okay? And so to kind of like build up the formalism here, I first want to start with the simplest possible model to gain intuition. Is a single qubit QPU. This is kind of like the smallest circuitry from the right-hand side that I can imagine that still makes sense. And it just is a single kind of like qubit wire. We have like some initialization where we can input a bit. Then we can do some single qubit logic, single qubit elementary gates. And then we read out, and then we get again a single bit. Okay? Yes?
I have a guess for why you write it this way.
Yes?
Correct. It appears as when you write computation of a function.
Yes. Very good. You didn't wait for the opportune moment, and it's not quite the same. But I would say kind of like when we buy a bottle of wine, you're definitely entitled to part of it, okay? Very good. Great, so this is kind of like the simplest case that I can think of, right? And I want to now use this to kind of like build up some intuition or maybe thwart your intuition about circuitry, because this is also important. We can also see challenges to the way we view information processing at this level already. Okay, but let's kind of like gain intuition. Here is a particular circuit that I can do. I can input a bit, imprint it onto a qubit, kind of like load it into my circuit. Then I can do a box, which I call math BBI, the identity. Then I read it out, and then I get an output that is exactly equal to the input. Okay? So just if this were a lab course on kind of like logical circuitry design and we would have quantum building blocks, then this would be the first building block I give you. And it's the identity operation, right? Kind of like O is equal to B is equal to the identity of B. So doing nothing is an option with a single qubit quantum computer. And this also means that you can in principle use it as a memory. You can store a single bit of information in a qubit and retrieve it reliably, at least ideally. Current hardware cannot do that yet. We're trying to make it better with error correction, but at least ideally this is a possibility. Another functionality takes a bit B as input. Then I use a physics-inspired X to denote it. It's very weird. You know it by a different symbol, but I can't change history and conventions. And this gives you the negation of B. So you can also have an elementary gate that negates the truth value. Flip 0 to 1 and 1 to 0. Okay? So the outcome is negate, not bit, and so this is negation. Okay? So these are 2 out of the 4 single bit functions I can implement, right? And I would argue it's the 2 that are interesting because they actually depend on the input. There's 4 single bit Boolean functions in total, but the other 2 are reset to a certain value. Forget the input and set 0, and forget the input and set 1. This is not something I can do here in this circuit model directly, but I could do it kind of like by forcefully resetting it and then restarting the circuit. Okay? But kind of like a nice observation is a single qubit QPU can do 2 out of 4 single bit functions. And this matters. Kind of like the two functions we can do are the ones that depend non-trivially on the input. Or, to make it stronger, and this will be an important constraint for quantum computing, these are the two reversible single-bit operations. These are kind of like the reversible. So no information is erased. The other two functions would erase information, and this is something we can't directly do on a quantum computer. You can build gadgets and tricks, but it's not easy. And just for completeness, I also like to write down the truth table. Here's kind of like the input value, and here's the output value. And then the truth table of the identity is this. And the truth table of negation is this. Right? And you know how to read that. We will revisit how to read that later on to generalize it, okay? So far, so easy, so boring. But I think it's a good start because this suggests that a quantum processing unit might be capable of executing classical Boolean logic, at least if it's reversible. So we are not making kind of like the computer worse. We are also not making it better yet. So here,
this is like the indicator function of the
what do you mean?
and the truth table should have, it's a single bit.
Yes, 0, 1, and a single bit output.
So you're just matching.
Yes. Sorry. Here is the first example which should surprise, maybe worry, and kind of like excite you. I can also kind of like make a circuit with a new elementary gate, which is now not Boolean anymore. Sorry, let me do it on this side again. I can start with a single bit entry, imprint it onto a qubit, and then apply a gate which is called H for Hadamard. And then when I do the readout, I get an O, an outcome bit, and this outcome bit is uniformly random. So if I write it like this, it's really, so it's 0 with 50% probability and 1 with 50% probability. Right? This might be mildly interesting for some of you, because in classical deterministic circuits, we cannot create randomness. Randomness is a powerful resource, but we always kind of like assume that we have to get it from somewhere else. This circuit apparently does it, and you might view this as increasing the entropy. That kind of like this gate somehow adds randomness to the bit value in order to bring a deterministic bit that initially was 0, 1 in order to be a random bit. So the way I would read that as a classical computer scientist or hardware designer is kind of like entropy increases, and we kind of like increase randomness. Okay? From this perspective, the next circuit identity, which is also true, and you could actually try it if I had a quantum computer with you, or you can try it with IBM quantum computers, which are publicly available. Something weird happens here. What happens if I apply this H gate twice, right? Should maybe, intuitively, it should increase the randomness further, right? But this is not the case. The outcome is exactly the input. So what this tells you is that this Hadamard gate, this is called the Hadamard gate. If I apply it once, it seems to randomize. But if I apply it twice, it cancels its action and does nothing. So this in particularly means that H is also reversible. And this is now strange, right? Kind of like, how can I have a reversible logical operation in any meaning that apparently induces randomness when I apply it once, but also gets rid of randomness if I apply it twice? Okay? And in order to kind of like really highlight the weirdness of this, I can also write down a truth table, but it will not look like a truth table anymore. So kind of like the truth table of the Hadamard gate looks like this. 1 over square root of 2 everywhere, and a minus sign in the lower right corner. And this should look strange for you, right? This is not the truth table of a legit Boolean function. Because truth tables of Boolean functions, if we in particular restrict ourselves to reversible Boolean functions, are permutation matrices. And what is a permutation matrix? A permutation matrix is a matrix that is orthogonal, so it's reversible, and binary. This truth table is still orthogonal. You can try it yourself. If you apply it twice, this 1 over square root of 2's are here to kind of like cancel the action, and you get back to the original. So this is still an orthogonal matrix, but you see that we dropped the binary condition. Okay? And it's also important that the two rows are distinct from each other, and there's a minus sign here. And this is the reason why kind of like the circuit can remember the original input. Because it maps kind of like what this intuitively means is it maps every input 0 and 1 to kind of like this entry and this entry are equally large. So it's kind of like both 0 and 1, but in two different fashions. This is 0 plus 1, and this is kind of 0 minus 1. And so it's kind of like it maps both inputs to combinations of the two bit values, but in a uniquely identifiable fashion. And this subsequently allows me to undo it. Okay? And with this, it's more kind of like pronounced in the lecture notes. With this circuit, this is one of the most elementary gates in quantum computing. You can actually do something that you classically cannot. You can build a random number generator. And this is one of the first commercially viable products that the quantum technology industry ever brought up. And they exist for a couple of years now. And I think in France and in Switzerland, there's companies who built these quantum random number generators. Because the laws of quantum mechanics tell us that this, if you build this properly, this should really be a random bit. Okay? Yes? Yes, exactly. Kind of like what this means is the initialization, and I will get to that now with the rigorous formalism. The initialization is kind of like deterministic and binary as you know it. The computation here is also in a way deterministic and reversible, but it operates on a different scale. Kind of like it operates on a level where it's not Boolean anymore, but you still kind of like you have more kind of like you have more continuous degrees of freedom. But up to here, there is no randomness. It's kind of like a deterministic configuration, but the readout is very disruptive and nonlinear. And so the readout effect is really kind of like what makes this work, because it forces possibly a combination of bit strings to collapse to a single bit value according to a distribution. And then you still, this is the only way to make it worse, to still get a bit string out, but possibly with randomness. Okay? So in a way, this is just imprinting digital information, loading it into the quantum realm. Here, we will have reversible logical operations, but with different degrees of freedom. And the readout stage collapses this more richer space of possibilities into one concrete bit string again, and possibly with randomness. Did this help? Very good. More questions or comments? I'm not aiming to convince you, and I hope that this kind of like thought experiment on the blackboard has maybe captured your interest if you don't already know this. You should really think about this as an electrical engineering lab course where we pretend to build boxes next to each other and see what happens. Okay? So now, let me go kind of like to the main part of today, is kind of like the mathematical formalism. For the single qubit. Kind of like how do we describe these phenomena with formulas? And how can we reason about it? And how can we in principle kind of like use math, ultimately it will be matrix vector multiplications, in order to reason about these circuits and how they should behave. Okay? And the important thing is the first definition. And this is the definition of a state vector, a quantum state vector. And this describes let's do it here. This state vector keeps track of the logical information within a quantum circuit. So it starts to exist as soon as we load information in. Here it is a very, very simple object. And then the state vector is acted upon by these circuits and gates. It changes itself like a bit vector when you pull it through, but it's a more general object, up to the very end. And then the entries of this vector will tell us something about the probabilities you obtain when you do outcomes. Okay? But formally, if we have a single qubit, there's two distinct values, 0 and 1. And kind of like a quantum state vector for a single qubit, a 1 qubit state vector is a vector which is sometimes called a ket. This is kind of like a weird prevalent notation in quantum computing. I want to write it down now. And in a lecture notes, I always write it down, but it's just a notation for a column vector. And it has two entries, psi 0 and psi 1. And I want to be very general now. I have no reason to be this general yet, but it's just a two-dimensional vector. And I want to kind of like keep all my options open. And so I give it continuous degrees of freedom and even allow complex valued entries. It's kind of like the largest field I can imagine. And we will later see whether this is necessary or not. But it's definitely kind of like, let's say, a rich enough object to store this. Okay? And we also need that this is normalized. So kind of like if I compute the length of this object, so kind of like these are two-dimensional unit vectors. Okay? And it has two entries. And I already suggestively labeled the entries with 0 and 1. And so kind of like this entry conveys kind of like the truth content or the amount of bit 0 in the circuit. And this conveys the amount of bit 1 in the circuit. Okay? So an example. And this is already an important part, is initialization. On the right-hand side, I said that we start with a classical bit and we imprint it into kind of like the state vector of a single qubit. Now with the definition of a state vector, I can make this precise. And if we initialize in 0, in ket notation you would call it 0 ket. If you like vectors more, which I do, you can call it E0, the first computational basis vector, kind of like encoding of 0. And this is 1, 0. And you should understand this as everything is concentrated at 0. Okay? And we also have the imprinting or loading in of the 1, which is the first standard basis vector. And this has a 0 on top and a 1 here. And you should interpret this as everything is concentrated at 1. Okay? So this is kind of like how you load information into a single qubit and how you can describe the current quantum logical state at the very beginning. Okay? This alone is kind of like not good enough, but I kind of like promised you that this tells us something about the logical content within such a circuit. And so this is a dynamic object that changes if I act with gates. Okay? So the next definition that we need is a gate action. A gate or circuit action. A single qubit gate is described by a unitary 2x2 matrix. U. And just to remind you, a unitary matrix is the complex value generalization of an orthogonal matrix. And an orthogonal matrix is a basis rotation. And a cool feature about orthogonal and unitary matrices is that they are reversible. It's really kind of like a rotation. I can go forward or backward. So this kind of like unitary encodes reversibility, an important constraint that I mentioned earlier. And by talking about unitary matrices, I kind of like do the same that I did with the state vectors. I kind of like assumed the largest level of generality I can think of. Again, complex valued entries, and then reversible transformation on that. We will later kind of like attack this kind of like assumption and ask ourselves if we kind of like with a discrete quantum circuit model actually get to the class, continuous class of unitary operations or not. Okay, this might seem overkill, but maybe it's not. Okay? And it acts on a quantum state psi in via matrix vector multiplication. So psi out is u times psi in, where this is a 2x2 matrix, this is a two-dimensional vector, and you use the matrix vector multiplication to compute that. Or in pictures, from right to left, I have psi in here, and I have psi out here, and now, yes?
Is it when we should say, oh, that's why you write from right to left?
Yes, exactly. Because linear algebra, matrix vector multiplication, and function composition, the way we learn it, is from right to left. And this is also why I write circuits from right to left, because what you can see now, maybe in the smallest example, is that this is really kind of like encoding a sequence of matrix vector products. Very good. You won. And you won as well. Okay? So far, so good. Let me do kind of like some simple examples. And in these examples, I kind of like compute the circuits that we did before. So kind of like, I can say the identity matrix, the gate that encodes doing nothing is really the identity matrix. And so for example, if I apply the identity matrix to, let's say, input bit value 0, it's the same as applying the matrix 1, 0, 0, 1 to 1, 0, and this is 1, 0, and so this is 0. Okay? And now I want to make you aware of something. This matrix was already above. It's the truth table you saw, but I just put round brackets around it. And let's do another example. What if, with negation, the matrix is this? It's again the truth table, put with brackets around it. And when I now apply it, let's say, to the 0 logical state, it's the same as 0, 1, 1, 0 to 1, 0. This is our vector representation of 0. And this is 0, 1, and this is our vector representation of 1. Okay? So I called this matrix vector multiplication, but it is in fact what you had to do in your hardware classes anyway. When you read a truth table and make sense of it, it's actually equivalent to matrix vector multiplication where you only work with binary vectors. Okay? So in a way, this formalism is, apart from the Z2 here, nothing new. It's just a linear algebra-inspired way of reading truth tables. Okay? And the same will be true when we scale up. The crucial difference is now that in this matrix vector formalism, we are not constrained to permutation matrices, to orthogonal matrices that are binary, but we may have a richer class where we can also do some continuous transformations. Okay? And this is the last example. If we take this Hadamard superposition gate, this mysterious gate here, then this is 1 over square root of 2, 1, 1, 1, minus 1. And suppose let's be fancy and apply it to the bit 1, to the initialization of bit 1. Then we have kind of like h initialization of bit 1 is 1 over square root of 2, 1, 1, 1, minus 1. 0, 1, so it's the second row. And so this gives me 1 over square root of 2, 1 minus 1 as the logical vector. And this is something you can't have with classical truth tables. It's kind of like it has non-trivial amplitudes or magnitudes in both. But you can also decompose this suggestively into a linear combination of the basic vectors that you know. Sorry, with a minus sign. And in physics notation, in quantum notation, this is sometimes written as ket 0 minus ket 1. And this tells you that in this qubit wire, after the Hadamard, there's a bit of 0 and a bit of 1. And there's also a negative sign in between. And if we instead did that with the 0 input, then we would have a 1, 0 here, and we have a 1, 1 here, and we would have an E0 plus E1 here. And so we would have a 1 over square root of 2, 0 plus 1 here. And you can see there's a difference in signs. And so even though both initial bit configurations that were deterministic get mapped somehow to both 0 and 1, they get mapped so in a fashion that can be reversed. Okay? And now if you really want to kind of like practice a bit, you can now apply this twice, and you will see that this will get mapped back exactly to the original one. Okay? But it's a bit too much linear algebra for me to do on the blackboard. Okay? So kind of like the next step would be that H times B is B again, by just multiplying another matrix in front, and you will see that you recover where you started from. Okay? And so this is really kind of like starting to break the rules just a little bit of what we're used to in classical logic. We're still reversible, but we allow kind of like for additional values. The last thing I need now is how to make sense out of these things, right? In the beginning, I promised you that a QPU, at least on a high level, is kind of like a digital device that eats bits and spits out bits. Now, these state vectors are not bits anymore. So we need a readout rule. And let me do that here. Here's kind of like a fact, or I don't know, postulate, which is associated with Born, one of the founding fathers of quantum mechanics. It's a physics-inspired principle, but it kind of like is the kind of like cornerstone of this, and it kind of like puts everything on a nice footing. The readout is probabilistic and destructive. This is not so important for now. I just want to emphasize it later because it matters for actual hardware. And so the probability of if I have, let's say, a quantum system in a state vector psi, and the question, the probability of obtaining outcome 0 is equal to the absolute value squared of the first coordinate in the state vector. And this is always a non-negative number. And likewise, the probability of obtaining outcome is 1 is psi 1 squared greater or equal than 0. And now you see why I had the unit vector restriction in the definition of a state vector. Because this tells me that the sum of these two is always 1. So this is guaranteed to produce a valid probability distribution. And maybe you can now see the structure working together. Kind of like the normalization in the beginning ensures that we start with a unit vector. Every single gate afterwards acts like a unitary matrix. So it rotates, but it doesn't change the length. So every single state vector remains normalized to unit length. And at the very end, in the readout stage, I do absolute value squared of these coordinates, and this gives me a probability distribution over bits. And it's a valid probability distribution. Okay? And just very quickly, when you actually do this in quantum hardware as we build it today, you really have to strongly interfere with the qubits in order to get classical information out, and this typically destroys or affects them. So just looking at the result of a quantum computation destroys the underlying logic. and gives you a sample from a random distribution. And so more often than not, you have to repeat the same quantum computation over and over again to get kind of like a new final state vector, sample from it, to get enough statistical information about your results. So this is kind of like really an intrinsic feature that the readout affects the quantum logic, and so you have to run quantum algorithms or quantum circuits many, many times. Let's do some examples. And the first example is again, let's read out when we did a negation and input a logical one, okay? We can now do the full pipeline. This is now a quantum circuit. We have all the rules, and we can check whether this really does what we expect, namely that the outcome is 0. Okay? And now after initialization, I have a state vector here. Psi 0 is 0, 1. We initialized everything in 1. Then we apply a negation gate to get psi 1. This is x 0, 1. We did it on the other side of the blackboard. This is 1, 0. And now we do the readout. And the probability of obtaining outcome 0 is 1 squared, and this is 1. And so we know the probability of obtaining outcome 1 is 0. So it's a deterministic distribution. So there's no randomness. And this explains why we could build classical circuits before. Because if we choose to, we can always stay in the digital logical binary realm and remain deterministic from beginning to end. But we can now do something else. And I will do it kind of like here. Now let me do it here. Here's the cooler example. What if we start in 1, apply this Hadamard gate, this quantum gate, and do the readout? Right? I had this on the blackboard already. Then psi 0 is again 0, 1. Everything is concentrated in 1. Psi 1 is Hadamard applied to this. We did the computation on the left-hand side. And this is 1 over square root of 2, 1 minus 1, right? And now what is the probability of obtaining outcome 0? It's the magnitude of the first entry, which is 1 over square root of 2 squared, which is 1/2. And what is the outcome of obtaining outcome 1? The probability is minus 1 over square root of 2 squared, and it's also 1/2, and this is the uniform distribution. So this is really a random number generator. And you can now start kind of like see that things are working together nicely because of the absolute values. The minus here doesn't change. So kind of like the minus doesn't affect the outcome distribution, but it is very much in the quantum logic. And so the Hadamard operation itself is reversible because on the quantum level we remember where we came from. But when we do this readout, we interact in a very destructive fashion and the probability distributions look the same. And so this apparent entropy in the middle of a Hadamard measurement is really a consequence of this probabilistic readout rule and not the underlying quantum logic. Okay? This is how you build a quantum random number generator. And this is also the effect that you might have heard in popular media as Schrödinger's cat. That it is both alive and dead. Kind of like many physicists love to tell this analogy of kind of like a box with a cat and some poison, and with some certain probability the poison fires off, or it doesn't. And they use it to explain the intermediate logical step after applying a single Hadamard gate, where you have this 0 plus 1, dead or alive. But then they stop. And this frustrates me, because if you give me a box and you tell me there's a cat inside and it's either dead or alive, I'm a practicing Bayesian. I have no idea about it, so I would say with 50% it's dead and with 50% it's alive. And so I wouldn't quite understand how me looking into the box should affect kind of like the state of the cat in question. Okay, somehow this is not the part, but kind of like what this analogy tells you is after a superposition gate, you have both 0 and 1. And if you choose to measure then, it's really a random process that gives you one of the outcomes. But this could still be explained with just basic Bayesian reasoning. What is surprising about the Schrödinger cat example is that I can save the cat again. I can start with an alive cat do a quantum operation to force it into a superposition of both dead and alive. If I were to choose to measure then, to do the readout then, I might collapse it, and it's a 50% chance that it dies, but I can choose to undo that. And this is the surprising effect, because Bayesian reasoning cannot explain this, that I can kind of like act on it and reduce all uncertainty from it. Okay, so kind of like what we did now is not only the first commercially viable application of a quantum processing unit, a random number generator, but also a mathematical formalism to really reason about Schrödinger's cat. Is there questions or comments at this point? Doesn't seem to be the case. Yes?
Are there different readout rules, or is this like the model?
This is the standard model in kind of like the current quantum computing design. This is something that every hardware has to obey. And I think it is also universal, in the sense there's more general measurements that I can do. And this is an interesting study, but I can always mimic or kind of like simulate these more general measurements by having a larger quantum computer with more outcomes and then coarse graining or post-electing. Like one chance I have, and this makes it much more expressive, is just think about a big quantum computer where I only use the first level to do single qubit logic, but I use all the other levels to kind of like get additional information in the readout, and then I can forget or post-elect on this, and then this gives me more expressive measurement rules here. So in a way, yes, and kind of like in physics, and especially mathematical physics, is a rich field of study, but there's theorems by Naimark, I think, that tell you that you can simulate it with circuits on a larger system. Okay? Very good. So this is the first kind of like illustration of how the basic rules of quantum work. And now, before moving on to larger QPUs, which will be relatively straightforward, I promise you, I want to go back and discuss my audacity of defining all these objects in a complex field. This is like very, very general. And I think it would be a bit embarrassing if we now figure out that there's only discrete values this can take, because then I overshot. Okay? So kind of like let us now look at gate sets and what's called universality. Okay? And this is very similar to kind of like classical logic and hardware design, where at some point I guess you learned that the basic logical operations negand, and or are complete in the sense that I can decompose every Boolean function in that way. Or we will take the opposite approach. How many functionalities can we create by combining very few elementary gates? Right? We could also in classical logic ask ourselves, what functions can we build with and, or, and negation? Okay? And so far, we have seen 3 quantum gates. Right? I showed you the identity, X, and Hadamard. Are all of these necessary for an elementary gate set, or is there one gate that I can create from the others? Well, I don't need the identity, right? This is kind of like either X squared, or it's also Hadamard squared, so this is not an elementary gate. And now we can ask ourselves, how many different functionalities can I reach by combining X and Hadamard? And what you can do, it's a good exercise, but there's kind of like, there are 4 functionally different circuits. What we can get is we have the identity, which is do nothing. We can do negation. We can do Hadamard. Maybe it's more than 4. We can do Hadamard X Hadamard, which for those of you who had the quantum course already is Z. It's the Pauli Z matrix. It's a sign shift. And then we can do X Hadamard, which is X times Z, and this is approximately the Pauli Y matrix. And then we might also be able to get HX and XH, but that's it. more or less. So kind of like there's not many functionalities. It might be wrong in the lecture notes, but I think there's 6 or so. And then it starts kind of like repeating itself. Okay, so kind of like there's no emergence of complexity or continuous degrees of freedom. In a way, it's a very, very restricted set of operations, and if I may write it here, if we kind of like try to envision just a crude sketch, and I don't have time to get into it, but state vectors are kind of like continuous objects in 2 complex dimensions. That means it has 3 real value degrees of freedom. They're unit vectors, so they kind of like correspond to objects on a sphere. And what you can get with these gates is you can get logical 0, you can get logical 1, you can get the Hadamard states, and then you can get kind of like other states. Kind of like there's 6 different logical configurations I can reach, because they form a group, and so kind of like patterns repeat themselves. Okay, so this is very much like classical logic. Still very discrete, 6 different objects. So if you want to really kind of like unlock more continuous degrees of freedom, we need more gates. Okay? And these are kind of called Pauli gates. But we can add additional gates. And one popular choice is the so-called Clifford gates. Where we take Hadamard and X, these are the 2 generating gates we had before, and now we add 1 additional gate, and it's called the phase gate, and it looks like 10I. So it has a complex number on the lower diagonal. This is still a unitary matrix, but it's not orthogonal. And this is something that I can add to our toolbox. This is something that quantum hardware providers can do. Okay? And now these 3 gates generate a group, the so-called Clifford group, with 24 elements. Right? Kind of like you can do it yourself, maybe write some software here. It's just basic matrix matrix multiplication here, but you can get 24 distinct functionalities. Maybe not so surprising, I increased my gate set, I get more gates, but it's still very, very finite. Like 24 is closer to 2 in the classical realm than infinity, right? So let's maybe see whether we can push this further. And now what happens if we take Hadamard X, and I will take 1 more gate, the T gate, which is 1, 0, 0 exp of I pi over 4. And this is the same as 1, 0, 0, 1 square root of 2, 1 plus I. Okay, this is now a real complex number that has both a real and an imaginary part. And for those of you who remember the complex unit circle, this is kind of the square root of this. If I square this guy, I get I. So kind of like, you can now maybe see a pattern because this S gate is the square root of the Z gate. So kind of like I started with gates, then I took a diagonal one, and then I'm taking square roots to see how much this enriches. Kind of like the functionalities, okay? So this is T squared is S. And now, who of you thinks that we will get a larger finite number? That this pattern continues. I add more gates, and so kind of like I get more elementary gates, so I get a larger functionality, because the square it is S, so I can in particular create these 24, but I can create more gates potentially because I have this T gate. How much more? Who thinks that it's kind of like a controlled amount? That it kind of like becomes a larger number but finite? Really nobody. This would be my guess. Very good. Who thinks that this increases the reach in an unbounded fashion? Very good. You're all right, and you would beat young me if I were to hear this for the first time. There's a beautiful theorem which in its most powerful form is due to Solarway and Kitaev, that tells you Hadamard X and T and if you're kind of like careful, you don't need the x because you can generate it from Hadamard and T-gates, can approximate any 2x2 unitary U. This is surprising for me. Kind of like we have two elementary gates, discrete. It looks very much like elementary basic logic, but when I start combining them and make the sequences longer and longer, I can really reach every point on the manifold of unitary 2x2 matrices. Okay, so we can approximate any unitary, and this is the surprising thing, which is due to Solovay-Kitaev, and to get approximation accuracy epsilon, you only need order log to the z 1 over epsilon gates. And c is, I think, somewhere between 1 and 3 plus O of 1. Okay? So not only can you reach every possible unitary, but the numerical precision is very similar to what we are used from floating point arithmetic, up to this c. If I want to get epsilon close to any target unitary, the number of gate combinations I need, the sequence length, the size of the circuit, only scales polylogarithmically in 1 over epsilon. And this depends a bit on the choice of gate set, but if we take Hadamard and T-gate, I think the C is 3 plus O of 1. You can take larger, more expressive gate sets, and then this drops down to 1. But for me, this is a very surprising result. No, it's an upper bound, kind of like. No, I'm not aware of any. I think this is an interesting and active field of study. I just know the upper bound here. And there's other gate sets where I think we can achieve 1. And the proofs basically use group theory. Kind of like the Clifford group is a proper group, and it's a maximal subgroup of all unitaries. And so if you add just one additional gate that it's not in the group, you have kind of like this effect that you reach everything. For me, the analogy, yes?
Can you provide an example of how you would combine these gates?
No, this is a very difficult problem. Kind of like there is kind of like ad hoc solutions. And the way to prove this, how Solovay and Kitaev did it, uses commutator relations, and so it's a sequential buildup. But kind of like the actual algorithms are not efficient. And this is a big open problem.
Wait, you're saying that there's no known efficient algorithm where I give you 1 qubit gate and approximate it up to n bits, right? Like these complex numbers I give you.
Well, I think let me not too, sorry, maybe I was a bit rush here. I think maybe for the single qubit case you can do it. And I would argue the proof of the Solovay-Kitaev theorem is already a template on how you could do it. We can ask the same question for n-qubit circuits, for big unitaries, and then it's very difficult.
No, but then that's like automatic programming.
Yes.
We don't expect that.
Yes, exactly. So, sorry, thanks. In general, this is a hard problem for the single qubit case. I think it is doable.
No, I was surprised at that because it's not constructive.
No, it is constructive, kind of like with commutation relations. But I think it's kind of like, I once gave it to a practical kind of like hardware designer, and they said, what is this? So kind of it's very far from a practical algorithm. Very good. Okay. Thank you for staying with me. The next part of the journey is just scaling up. You've seen kind of like all the essential ingredients for a single qubit system. You've seen the underlying formalism. What we will now do together, and I will do it very quickly and very sloppily, is to explain how this works for n-qubits. It's a bit like in normal logic where you first start with single bit logic and then you go to n-bit logic. Nothing fundamentally changes anymore. Okay? To n-qubit. Okay? And now what is a state? And in order to introduce what a state is, let us think about kind of like how the complexity or the richness of the logic changes. The state vector for the single qubit system was the most essential kind of like building block, and it had 2 coordinates because we had 2 distinct bit values, 0 and 1. Now if we have n bits, we have 2 to the n distinct bit values, right? So kind of like n bits, 2 to the n distinct bit strings. This is how kind of like complexity emerges in logic. And each of them has to be a valid input configuration for our quantum system, for our quantum computer. And also what I expect from an n-qubit QPU is that it is an n-bit memory. So I must be able to store any of these 2 to the n bit strings, and I must be able to recover it if I don't do anything in between, right? But I can do things in between, and we've seen that before. So like the only way of making this work is to have really big state vectors. And so kind of like the definition of an n-qubit state vector, this is again a vector, but it's now a linear combination of all possible kind of like bit configurations. So kind of like I have an amplitude or a coordinate assigned to each possible bit string labeled by EB, and when I write this as a column vector, I start with psi 0, 0, 0, 0, 1, and psi 1, 1, 1. And you see that this is an exponentially large vector, okay? So fundamentally nothing changes, but it becomes really cumbersome to store that. Yes?
I just have a question about accuracy epsilon.
Yes?
Is it about the coefficient of the matrix U, or is it about the probability you get after measurement?
Well, what you do is you take the operator norm difference between the two unitaries, because formally this bounds the maximum total variational distance I can have between the outcome distributions. So you're kind of like using a norm, a matrix norm, the operator norm, kind of like the spectral norm, because this bounds the largest deviation between the two unitaries for every state vector. And with the probability rule, this in turn bounds the largest deviation between the two kind of like probability distributions. So operator spectral norm in the matrices ensures epsilon closeness in spectral norm, ensures epsilon closeness in the total variational distance of the outcomes. Great question. Okay. And now you can already guess what is an n-qubit circuit in general. The quantum logical part in the middle. Before it was a unitary 2x2 matrix, what it's now. It's a 2 to the n by 2 to the n unitary matrix, right? U. So the same system prevails, it's just exponentially more difficult. And kind of like the rule is the state after the circuit is matrix vector multiplication with the state before the circuit. Okay? And then what we have is the readout rule. And this is again due to Born. And this is now also a multidimensional generalization from what we've seen before. We now, if we have such a state vector, we now have 2 to the n different possible outcomes because it's a bit string, and the probability of obtaining bit string W is equal to the coordinate in this huge state vector that is associated to the bit string. And I should also say that this is normalized. So, the same as before, it's kind of like a unit vector. And this is greater or equal to 0. And if I add up all of these absolute value squares, I recover the length squared of the original state vector, and this is 1. Okay? And a simple example is to build an n-bit random number generator, where you kind of like, I leave that to you if you're interested. Just look at the following circuit, where you initialize in any bit string, then you do Hadamard gates on each of the guys, and then you do the readout. So this is not very readable, but what I'm telling you is look at the random number generator from before, which was a single qubit thing, and do it n times in parallel. Then you get a very simple n-qubit circuit with an n-qubit input state, unitary, kind of like gates. and you will get a uniform outcome string of bits. Okay? Now, how do we build these unitary circuits? Kind of like, this is now a general unitary here, but this is just what we can reach. What we actually do is visualized here. We take elementary gates and combine them to get more expressive functionalities. And we already know what gates we need. So kind of like here we need an elementary gate set. And I think a good starting point is if we allow ourselves this Hadamard and T gates for every single qubit. But this is clearly not enough because these are single qubit operations, so they have no conditional power. If we really want to explore this larger space, we need some conditional operations, some way to couple the qubits. And I've already written down some here. The most popular choice, arguably, is in gate language. It looks like this, and this is the control, and this is the target. And this is a reversible XOR. So if I have bit A and B as input, then the output A survives, but its content is XOR to the second wire. So we have an XOR between the two input bits on the second wire, and the first wire survives to ensure that this is a reversible implementation. Okay? So this is again a classical logical operation. Just reversible XOR. In quantum computing, you call this a Z-NOT gate. Okay? So these are, I think, a natural starting family for a universal gate set for these n-qubit devices. 2 single qubit gates, 1 2-qubit gate. And then this is universal in the sense that you can approximate any 2 to the n by 2 to the n unitary. Okay? So if I start building circuits like this, I can again reach any unitary in a now exponentially larger space. It's similar to before, but maybe even more surprising. Because we really have a 2 to the n by 2 to the n matrix. There's 4 to the n entries. They are kind of like 4 to the n degrees of freedom roughly. And you can approximate all of them with these elementary gates. And here, we don't have efficient algorithms. Okay? Just because I'm running out of time, you also need matrix vector multiplication rules to take these small gate descriptions that we had. Like a single Hadamard gate is a 2 by 2 matrix, and somehow blow it up to have the dimensionality of these big unitaries. And there's like nice matrix operations that do it. For example, you can decompose your quantum circuit in sequential layers. And then each layer is described by 2 to the n by 2 to the n unitary matrix. And sequential application happens with the matrix product. Because remember, we do matrix vector multiplication to propagate the state vector. So the matrix multiplication tells me how to kind of like multiply together different layers sequentially. And then there's another beautiful product called the Kronecker product, which is a recursive application of matrices. Kronecker product A times B is kind of like a block matrix where you kind of like print the block B at every position of A and scale it with the coefficient. This Kronecker product can be used to merge parallel layers of gates. Okay, and you can quickly convince yourself that if I take a Kronecker product of n 2 by 2 matrices, I get one 2 to the n by 2 to the n matrix. And this is how you kind of like build up these layers and actually in principle can compute these big matrices. Here the first layer has like a C0 on the first 2 qubits, then nothing, then a T gate here. I can build Kronecker products to build the big 2 to the n by 2 to the n matrix. And then I can keep going. Okay? The lecture notes have this in more detail. But this is roughly what I wanted to convey today, which is, hopefully I succeeded there, kind of like the ambition and the reason why people like me and Alex care about these objects. You can really do more things. And the surprising thing is the Solovay-Kitaev theorem for me. You can really start kind of like almost digital with a finite gate set and get continuous degrees of freedoms and very good approximations. Okay? And we also have a mathematical formalism to reason about it. So we can, in principle, there's no unanswered questions. The entire problem is a problem of scalability. If you make these quantum processing units larger, the matrices become larger, and even server farms run out of memory. And this is what people do, or research groups do, when they try to simulate, classically simulate quantum processing units. Okay, and I think for me, this is in theoretical computer science terms, this is an important observation. Because what I showed you with this matrix vector formalism is that you can do everything a quantum processor can, you can also do on a classical computer with an exponential overhead. That means quantum computers don't change the grand scheme of computability. The halting problem remains difficult. What it can change, however, is kind of like the resource cost of solving problems. And there I also showed you implicitly that a quantum processor can do everything a classical processor can do. You take the circuit description, you implement it reversibly, you can do that with a linear overhead, and then you can run this reversible classical circuit on a quantum computer. So quantum processing units are at least as powerful as classical processing units. And if we want to simulate them, we have at most an exponential overhead to pay on classical hardware. So quantum processors are really kind of like between polynomial and exponential scaling, but we don't expect them to change the grand scheme of things. But there is interesting problems that fall into this category, and a famous one is integer factorization of two prime numbers. There, Peter Shaw in 1994 first reduced the problem of integer factorization to the problem of finding order, the order in modular arithmetic, and there he found a quantum circuit that with constant probability, I think, finds the order of this number in a number of steps that only grows like the cube of the bit description. And so this can be viewed as a probabilistic but efficient algorithm for integer factorization. Beyond this, not so much is known. And another reason, but this is more interesting for physicists, is this theorem here. They're kind of like these small gates, Hadamard, T, and C naught, are universal in principle, and they allow you to approximate any unitary 2 to the n by 2 to the n unitary. Why do physicists care about that? Because they really like their Schrödinger equation. The Schrödinger equation describes the time evolution of a quantum system and is notoriously difficult to simulate on classical computers. But by definition, if you assume that the Hamiltonian is time independent, the system is closed and finite dimensional, the time-dependent Schrödinger equation implies that the solution is a big unitary 2 to the n by 2 to the n matrix. This is just a consequence of the Schrödinger equation. And what's written here is that you can simulate any of these unitary matrices with discrete quantum gates. And now this is getting interesting. So in principle, these QPUs are also universal simulators of solutions to the Schrödinger equations of quantum physics with a finite number of degrees of freedom that is smaller than 2 to the n. Okay? And this is what people mean when they want to use quantum computers for simulation. There's, however, a big catch that you might guess already. A generic 2 to the n by 2 to the n unitary has a huge amount of degrees of freedom, and it will be exponentially costly to approximate it with these types of circuits. And we will discuss exactly these arguments in lectures 2 and 3. Thank you very much.